Welcome to Quantum Field Theory 1. So this is the first in a sequence of quantum field theory courses. And before I give you an outline of this course, I just want to say a few words about why we need quantum field theory. So just going to give you a few reasons. There are many others, but just as some motivation. So quantum mechanics and special relativity imply that particle number is not conserved. So the reason for this is that the uncertainty principle tells us that if we try to put a box in a particle in a box, then there is some uncertainty in the energy of that particle. Particular uncertainty in the energy is bounded below. The box has size L. So quantum mechanics tells us there's some uncertainty in the energy. But on the other hand, Einstein's special relativity relates mass and energy. So if we make the box small enough, we can make the uncertainty in energy large enough so that we have enough energy to create a particle-antiparticle pair. So if delta E is 2 mc squared, then we can create a particle-antiparticle pair. And there's no way to deal with particle non-conservation in ordinary non-relativistic quantum mechanics. So we need something more general. A second reason that we might want to study QFT is just the existence of identical particles. So in non-relativistic quantum mechanics, there's no explanation for why all electrons are the same, or all photons are the same, or all neutrinos are the same. This has a very natural explanation in quantum field theory, because all particles of the same type are just excitations of the field corresponding to that particle. So the electrons are excitations of the electron field for existence, for example. And so the existence of identical particles begs an explanation, and it's very naturally explained by quantum field theory. A third reason why we might be interested in QFT is locality. So in classical mechanics, in order to avoid action at a distance, we introduce fields. And so if we want to have a local quantum theory, that suggests we should, or one of the easiest ways to do that is to introduce fields. So these are just a few of the reasons why we might be interested in studying quantum field theory. It has applications in many areas of theoretical physics, from particle physics to condensed matter. I will talk, and Tibor will talk in the second half of this course about some of the applications to particle physics. And in other side courses, you'll see applications of the ideas in this course to many other areas of physics. So that's just a brief motivation for why we might want to study quantum field theory. Before we get started, I just want to give you an outline of what we're going to cover in this course. So quantum field theory is a broad subject, and We won't cover everything in this course. So let me first just give you a very extremely brief outline, and then I'll go into some more detail for, about what's going to be covered in the first half of this course. So Tibra and I have divided the course in half, so I will be lecturing for the first half of the course. Tibra will lecture the second half of the course. And we have decided to divide things up by spin. So for the first half of the course, we will focus exclusively on spin-zero particles and the associated scalar fields they come from. And in the first half of the course, we'll just we'll quantize the scalar field and develop a lot of the formalism of quantum field theory. And then Tibra will tell you about what changes when we introduce higher spin fields. So that's the extremely brief outline. And let me go into some more detail about what I'm going to talk about during my half of the course. So the main goal, or a main goal of my half of the course, is to relate quantum field theory to observables. So we're going to spend almost the my entire half of the course trying to relate trying to compute observables in scalar field theory. So that's going to take us 6 or 7 lectures. And so we'll start out today reviewing some relevant classical field theory. And then tomorrow, we will quantize the free scalar field. And then the next 5 lectures will be devoted to adding interactions and seeing how that changes the picture. So on Thursday, we will study the LSC reduction formula, which relates scattering amplitudes to time-ordered products of fields, and I'll explain more what that means when we get there. Then we will learn how to compute time-ordered products of fields. On Friday, we talked about the interaction picture and Wick's theorem. Then next week, we'll learn a different but equivalent way of calculating scattering amplitudes. And finally, we'll relate scattering amplitudes to observable quantities, such as cross-sections and decay rates. And in the final lecture, we'll have a brief introduction to what happens beyond leading order in perturbation theory. The way we're going to calculate cross-sections and decay rates and scattering amplitudes is all going to be perturbative. And some interesting things happen beyond leading order. If you've heard of renormalization, we'll have a brief discussion of that in my final lecture and a much more thorough discussion in QFD2. So that's where we're going. And before we get started, I just wanted to.
So your final lecture is what?
Is next Wednesday.
A week and a half instead of 1.5 and a week and a half.
Yes, 7 lectures on spin 0 and 7 lectures on spin half and spin 1. Any questions? And so throughout this course, we'll use natural units, where h bar and c are set to 1. This means that energy and mass have the same units. Normally, we'd relate them by a factor of c squared. We'll just set c equal to 1. This is a convenient choice of units. And you can always go back and put in the missing factors of h bar and c by dimensional analysis. All right, so for the remainder of today's lecture, we will discuss classical field theory. And basic object of study will be a classical field. Is a function of space and time, which I'll also denote by 5x. So the x without an arrow on top has 4 components, and the x with the arrow is just the spatial part of the other x. And so we can think of a field as a generalization of a collection of generalized coordinates in classical particle mechanics. So A here is a label that runs over the however many coordinates we have. And we can think of x here as just a continuous label. So here we have infinitely many degrees of freedom. At least 1 per point in space. So if it's just a single field, then we've got 1 degree of freedom per point in space. I'm just thinking about this analogy where A becomes continuous. But we could have more than 1 field, in which case we'd have more than 1 degree of freedom per point in space. And so note that the approach we're taking is that we are demoting position to a label. In quantum mechanics, it's an operator. But we're trying to construct a relativistic theory. So it seems like a good idea to treat space and time in the same way. So there are two approaches you could imagine. One is that we could demote position to a label, which is the approach we're going to take. The other one is we could promote time to an operator. And that works out to be a little more complicated, but in the end, you'd get the same results. And string, one approach to string theory takes basically a similar approach where time is promoted to a label. But we're going to take the opposite approach and demote position to a label.
Sorry, just a question. So the x on the right side, it is both time and space variable, or?
Yes, this x is the same as Tn.
Okay.
So this is it's 4 components. Okay. So the basic object of study in classical mechanics is the action, which, for many purposes, you're interested in an action that has the following form. It's just a function of the generalized coordinates and their first time derivatives. And similarly, we're going to be interested in an action that has the following form. Okay. So this is not the most general action we could write down, but we're going to restrict our action, our attention to actions of this form, because this action has several nice properties. So first of all, we're going to restrict. Okay. So first of all, here this curly L is what's known as the Lagrangian density. Which, if we just integrate the Lagrangian density over space, we get back the ordinary Lagrangian. It's very common, and I'll probably do this several times, to refer to the Lagrangian density just as Lagrangian. But by context and the notation, it should be clear which is which. So this action has several nice properties. So first of all, we're going to demand that the Lagrangian is Lorentz invariant and only contains 4 derivatives of our fields. So we could imagine writing down something where we have different numbers of time and space derivatives of our fields. If we do that, what we end up with is probably not going to be Lorentz invariant. So we'll restrict our attention to Lagrangian densities that only depend on this combination of derivatives. And furthermore, only on the first derivatives of the fields for now. Secondly, this Lagrangian enforces locality. So we only have a single integral over space here. There's no, you can imagine writing down something that's like integral d3x, d3y, and there are fields here that depend both on x and y that interact. If we write down an action like that, it's not guaranteed to be local. So there may be contexts where actions of that form are interesting, but we'll restrict ourselves to manifestly local and Lorentz invariant actions.
And why wouldn't we use, for example, box of this scalar?
So if we, well, of course, if we could integrate by parts to move maybe a second derivative onto here. But in general, if we have more derivatives, you can run into problems. The theories can be unstable. They can have negative norm states, for instance. So in general, there are exceptions, but in general, theories that have more derivatives, you have to be more careful. They may not make sense quantum mechanically. OK. So one example of a field that you're all familiar with is the vector potential from electromagnetism. But that, as its name suggests, transforms as a vector under Lorentz transformations, which makes its quantization more complicated. Tibor will tell you about it near the end of the course. But we're going to stick to scalar fields in my part of the course. So scalar fields transform as follows under Lorentz transformations. And I'm going to use active transformations so that I have a minus sign here. So here, lambda, so this is just to establish the notation, under x mu goes to x prime mu where lambda is a Lorentz transformation, which means that it leaves the Minkowski metric invariant. And we're going to use the convention that the metric is mostly negative. And so this minus sign comes from the fact that we're using active transformations. So an active transformation means that thinking of the observer or the origin of the coordinate system is actually rotating. So for instance, in my coordinate system, this piece of chalk is directly ahead of me. If I rotate by minus pi over 2, the chalk is at plus pi over 2. So that's what we mean by an active transformation. Okay. And the simplest theory that involves a scalar field and has a local Lorentz invariant action is known as the Klein-Gordon theory. And this will be our main example for some time. So the Klein-Gordon Lagrangian density, or just Klein-Gordon Lagrangian, is this involves two terms. So this Lorentz invariant combinations of the derivatives of phi, and then a mass term. And so again, remember we're using units where h bar and c are 1. So time and space derivatives have the same dimensions as mass. Okay. So one of the most basic questions we can ask about this theory are, what are the equations of motion? So in classical mechanics, classical particle mechanics, we find the equations of motion by setting the variation or the functional derivative of the action with respect to the coordinates equal to 0. And this gives the Euler-Lagrange equations. As you're all familiar with. So remembering our analogy between classical particle mechanics and classical field theory, suggests that the way to find the equations of motion classical field theory is just to set variation of the action with respect to the fields equal to 0. And this gives, again, assuming that our action has this form, that this gives the equations of motion. And just like in classical mechanics, we can also we can have more than one coordinate. In field theory, we can have more than one field. So if we have more than one field, we could just add an index or a subscript to our fields. And we just have the same equation for each of the fields. So for the Klein-Gordon theory, we can compute the equation of motion given our Lagrangian. So this first term just gives us m minus m squared phi. The second term gives us a minus d mu phi equals 0. And we can just multiply everything by -1. And this is our Klein-Gordon equation of motion. And we'll solve this near the end of lecture today. OK. So one important result that we'll come back to not only in this course, but several other courses. I think you've seen in a different context in the front end. But just want to make this explicit when we're dealing with field theory. And that the result is Noether's theorem. And Noether's theorem states that every continuous symmetry of the action gives rise to a conserved current. And here, conserved, this means that d mu, j mu is 0. So this is a very important result. It's an entirely classical result. So often it will work quantum mechanically, but as we'll see in QFT3, there are some subtleties when we try to write down a quantum mechanical analog of this statement. And we'll discuss that in much more detail in QFT3. OK, so conserved, we have a conserved current that implies a few different things. So first of all, conserved current, if we have a conserved current, we also have a conserved charge. And to see that, we can just define a charge, which is the integral over all of space of the zeroth component of the current. And say a charge is conserved if its time derivative is 0. But if we compute its time derivative, we get it's just the integral of dj0 dt, which, using the conservation equation, d mu j mu is 0, tells us that this is just minus the integral d3x of the divergence of j. And this is 0, assuming j goes to 0 sufficiently quickly as x goes to infinity. We can just write this as a surface integral. Furthermore, we have a conserved current, and not only tells us that the charge is conserved overall, it tells us that charge is conserved locally. And to see that, it's almost the same derivation as we just did. We can define the total charge enclosed in some volume to be the integral over that volume, d3x, j0. So we've got some volume here. And it's bounded by some surface A. And there's some normal the surface, ds. Then these two steps don't depend on the area we're integrating over. So that just tells us that dqv dt is minus the integral over a of j dot ds. So the rate of change of the charge enclosed in some volume is controlled by the flux through the surface. Okay. So why is Noether's theorem true? We sketch a proof. So if we have a continuous symmetry, then we can consider infinitesimal transformations. So then we'll consider we've got some collection of fields. So A is here labeling which field we're talking about. And then under the symmetry, the fields transform into some function of all of the fields. So note that if we had a discrete symmetry, we couldn't necessarily write down the infinitesimal version. But as long as we have a continuous symmetry, we're guaranteed that we can transform the fields infinitesimally. That's what we mean by a continuous symmetry. And we'll say that this is a symmetry transformation. If the variation of the Lagrangian, if we do this transformation, is a total derivative. So you might expect that I was going to write 0 here. We'll allow a total derivative because if we have a total derivative over here, then the equations of motion won't change. Yes.
And why don't we also change space-time coordinates? Like we make the transformation of space-time, or just a variation on our field?
So we could consider a transformation that is space-time dependent, or we can consider an internal transformation. In a few minutes, I'll go through an example of both kinds. So it works in both ways. Was there another question?
You have to consider that's a variation in the functional form, right? But what I'm trying to say is, like, for example, if you consider like Lorentz symmetry, like since those are scalars by definition they don't transform, but there is a transformation in their functional form, and that's the one we're interested in. Right?
That's right.
Okay.
So certainly we can choose f to be 0. So if the Lagrangian is invariant, then even if some or all of the fields don't transform, that could still be a symmetry. Okay. So to see where Noether's theorem comes from, let's consider an arbitrary transformation of the fields. So we're not yet imposing that this variation in the fields is a symmetry. We'll do that in a minute, but for now, we'll consider this to be an arbitrary transformation. So under an arbitrary transformation, the Lagrangian will just change as follows. So we'll get two terms. Again, assuming that our action has this form, it only depends on the fields and the first derivatives. So we'll get one term from the variation of the fields and a second term from the derivative terms. And so far, this is basically the same procedure. You use to find the Euler-Lagrange equations. And like we do in that derivation, we can just move the derivative off of this term and over here onto to this term. I'm using the product rule. And what we get this term, nothing happens. We get a minus d mu partial So these two terms times d phi a, and then we get an extra term, which is and so this term should look familiar. This is just the equations of motion on the bottom line of the top board. So if the equations of motion are satisfied, then this term is 0. So when the equations of motion are satisfied, only this term survives. And now we can set d phi a to be equal to ya. So now we'll assume that the transformation is a symmetry. Then what we have is delta L is equal to d mu dl d mu phi a times y a of phi. And also, if this is a symmetry transformation, then we know that the Lagrangian density changes into a total derivative. That's what we just called d mu f mu. And so both terms are now total derivatives, which is precisely what we wanted. We wanted to find a conserved current. And conserved current means that d mu, j mu is 0. So if we just move both these terms over to the same side, we found our conserved current. So then d mu, j mu equals 0 if j mu is dl d mu phi a ya of phi minus f. So we've not only shown that there is a conserved current, but we've found an explicit formula for it. So let's look at a few examples to see how this works. So first example, the space-time symmetry, just space-time translations. New. Under the infinitesimal space-time translation, phi a of x should go to phi a of x. The first term in the Taylor series would just be epsilon nu d nu phi a of x, and then the higher order terms, which we can neglect. So the fields will just transform like this. And note that the plus sign here comes from the fact that we're using active transformations. So the same argument tells us that Lagrangian transforms basically the same way. Lagrangian is a space-time scalar as well. Transforms in the same way. So here we've got 4 independent space-time translations, one for each direction of space-time. So we could apply Noether's theorem independently for each of the independent directions of space-time. So we expect that there are 4 conserved currents instead of just 1. And we can find them just by using this formula here. So all we need to do is to compute this derivative of the Lagrangian, figure out what f and y are. And we've already done most of that. We just computed y and f. So all that's left to do is compute this derivative. Or, well, without any more assumptions, we can't do that, but we can. So we can just plug in our results. And what we get is that on there. So what have I done here? So here I have plugged in for y. So y is just this term here. Y is how the fields, the infinitesimal change in the fields, if we do an infinitesimal symmetry transformation. And here, this term is f. So epsilon times L is just f, and that's the term here. And note that both epsilon, both f and y depend on epsilon. So I put an epsilon over here. If a current is conserved, then any constant times that current will also be conserved. So I can just multiply the current by epsilon nu, which allows me then to cancel this out off. This conserved current is what's usually called the energy momentum tensor. which you're probably familiar with from relativity. And the conserved charges associated with this conserved current is the Four momentum. P mu, which is just the spatial integral of T0 mu. So again, there are four translations, so there are 4 currents and 4 charges. So that's an example of a space-time symmetry. Oh, sure. More? Okay. Is that better? Oh. All right. Okay. So I want to go through another example. It will be important later in the course, which is the example of a U1 internal global symmetry. So here, internal just means that transformation doesn't depend on space-time, and global, the internal means it's not a symmetry of space-time, and global just means that the symmetry parameter is a constant. It's not allowed to depend on space-time. So in Tibor's part of the course, you'll learn about a gauge U1 symmetry, where the symmetry does. Symmetry parameter is allowed to depend on space-time. Okay. So there's a wide class of scalar field theories that have a U1 internal symmetry. The simplest class involves complex fields. So we can write a complex scalar field. So sometimes it's useful to think of it as 2 real fields, one that's just the real part, and one that's the imaginary part. In tutorial this week, we'll look at in more detail at the scalar complex scalar field, and the simplest Lagrangian we can write down for a complex scalar field that has a U1 symmetry takes the following form. So it has a derivative of phi star, derivative of phi, and then some potential term that depends on the magnitude of phi squared. Now, this Lagrangian has a symmetry if we redefine the phase of phi. So if we redefine the phase of phi as follows, so that phi gets a phase e to the I theta phi, and means that phi star gets the opposite phase. Then this term is clearly invariant. These terms are also invariant as long as theta doesn't depend on spacetime. Then it just moves past the derivative. So this Lagrangian is invariant under this U1 symmetry. Note there's no 1/2 here. This is essentially just a convention, but this will be the convention of not having a half will save us a lot of work later, and we'll see why in a few lectures. I just want to point that out, that I did put a half for the real scalar field. That's intentional. OK, so to use Noether's theorem, we need to write down the infinitesimal version of these transformation laws. And that's easy enough to do. So delta phi is just I theta phi. And delta phi star is just minus I theta phi star. Lagrangian is invariant. I just argued that the Lagrangian does not change. So delta L is 0. And with this form of Lagrangian, these transformation laws, we can read off y f, and in this case, we can compute dl dd phi. And so we get that, again, that the parameter theta times the current is equal to dl d mu of phi delta phi. But now we have, we've been treating phi and phi star as independent quantities. So there are two terms here. So here, so we're using the Einstein summation convention. So every time I have a repeated indice, it should be summed over. So here, this should be summed over if we've got multiple fields. So in this case, we're treating phi and phi star as independent fields. So we have a second term like that. And that's just the same with the star. And the last term is 0, because dl, variation in L, is 0. And we can compute these derivatives. And what we get is this derivative just gives us d phi, d mu phi star. This is plus I theta times phi. And over here, we have the same thing, just with a minus I theta. And the thetas cancel. And we just get the conserved currents right like this. And okay, so there's just one conserved current in this case. And the conserved charges, which may not be obvious from what we've seen here, but later in the course, we'll come back to this. So the conserved charges can have two different interpretations. You could either think of this as electric charge or as particle number. And we'll come back to that.
So because of the variation of the Lagrangian, we say that d mu f mu is 0.
Yes.
And why can't we take an f mu that is at the divergence-free field?
Taking some f that
A solution of d mu f mu is 0.
oh,
Strictly speaking, we kind of picked x mu to be 0 here because it was convenient. It's true.
Yeah.
You could pick something more exotic.
if we chose something else, such that d mu f was non-zero, we could get an extra term over here. That current would also be conserved.
So, but if we say that is the charge, if we have another term, we will have a different charge.
Yes. Yeah, we could write. This is a procedure that allows us to find a conserved current, but if you add two conserved currents, you get another conserved current. So there's in many theories, it's always not unique up to the multiplication, but it's often even less unique than that.
Isn't that also the probability current if you make those wave functions?
It could have. Yeah, the probability current would have a similar form.
Yeah, I guess it would be the spatial in this.
All right, so our approach to quantization is going to be very analogous to the quantization approach you're used to in non-relativistic quantum mechanics. It's what's known as the canonical quantization. So our approach is going to be to promote the field and its conjugate momentum to operators. And we'll do that at the beginning of tomorrow's lecture. So this is not the only approach to quantum field theory. And in quantum field theory 2, you'll see a apparently very different, but actually equivalent method of quantizing the field known as the path integral quantization. Both approaches have their advantages and their drawbacks. Some calculations are easier in one formalism, some are easier in the other. So it's worth learning both. One of the big advantages of the canonical quantization formalism is that it's very much analogous to what you're used to from non-relativistic quantum mechanics. But to use this approach, we need to develop the Hamiltonian formalism for fields, which fortunately is not very different from what you're used to for particles. So I'll just spend a few minutes going over that. All right, so again, just using our analogy, we can define the conjugate momenta to our fields, just as you might expect. So this is the momentum conjugate to the field phi a. And this is precisely what you'd expect based on the analogy with particle mechanics, where over here you just have a PA and here a QA. So nothing terribly surprising. One difference is that what you get when you multiply pi a times phi dot a of x and subtract the Lagrangian is not the Hamiltonian, but the Hamiltonian density. This is the Hamiltonian density. And we get the Hamiltonian just by integrating the Hamiltonian density, which, again, is not surprising if you remember that we're treating position as a label. It's like a continuous version of the label of the your generalized positions. So if you had many generalized positions, you would sum over them. Now we have a continuous number of labels of our generalized position, and so we just have to integrate over them. So not really very much new here. But it's worth pointing out just so we can write down the Hamiltonian for the Klein-Gordon field. So we take the Klein-Gordon Lagrangian, which I think I've erased by now. But we need to separate out the time and space components. If we're going to use the Hamiltonian formalism. And then we compute the conjugate momentum. And there's only one term that contributes. That's this first term. And so we get the Hamiltonian, then is the integral 1/2 pi squared plus 1/2 grad phi squared plus 1/2 m squared phi squared. Okay, so nothing is very complicated here. One thing that is worth pointing out is we've picked a time. So we're treating time and space differently. So only the time component was mattered when we were finding the conjugate momentum. And so there's something that is a little bit non-Lorentz invariant about our approach. In the end, we'll recover Lorentz invariant or Lorentz covariant results as we would expect. We're trying to construct a Lorentz invariant theory. However, it's not always going to be obvious. So that's one of the drawbacks of the canonical formalism. Basically, because we're treating time and space a little bit differently when we're going to the Hamiltonian formalism, it is not always going to be obvious that our results are Lorentz invariant. And so as a consistency check, we'll several times throughout the course be commenting on Lorentz invariance of our results. That one of the advantages of the path integral formalism that we'll discuss in QFD2 is that everything is manifestly Lorentz invariant, basically always at every intermediate step. That's not going to be the case here. Although, as I mentioned earlier, some calculations are easier in this formalism. So, okay. And, okay. The last thing I want to do today is to solve the Klein-Gordon equation. That will only take us a few minutes to get the first A solution to the Klein-Gordon equation. But we're going to spend a bit of time and effort to try to make our solution look as Lorentz invariant as possible. Basically to save us some effort later to mitigate this problem that I pointed out earlier, that things are not always going to be manifestly Lorentz invariant. And so by playing around with our solution now to make it as Lorentz invariant as possible, we'll save ourselves some effort later. This is just going to be a classical solution. Okay. So recall that our Klein-Gordon equation is d squared phi plus n squared phi 0. And the simplest way to solve this equation is to write phi, t, and x in terms of its spatial Fourier transform. And so the reason we're not transforming the time direction is we're going to take our solution and using the Hamiltonian formalism promote phi and pi to operators. And so we want to leave explicit the time dependence. And if we plug this solution, this form, this Fourier transformed version of the field into the Klein-Gordon equation, we can just read off the solution. And the solution will just be that phi of t and k is some function a of k times e to the I e k t plus some other function e to the I e k t, where ek is square root of k squared plus m squared. Basically, it's just independent wave equations.
One with the minus.
One is with the minus this. Here. Okay, so yeah, so this, we plug this in here. We just get the derivative, spatial derivatives just bring down a plus k squared. So that's where this comes from. So we get a minus sign from the I squared and a minus sign from the metric. Okay, so this is a solution. It's not necessarily a real solution. So we want phi to be a real scalar field. We've got a bunch of i's floating around here. So this is not, it's not obvious that this is real, and in general it's not. So if we want phi to be real, then we want phi to be equal to phi star. And phi star is of p and x is equal to the integral d3k phi cubed e to the minus I k dot x tilde star. And so if we want to compare this equation to this equation, we should take k to minus k so that we can, so we have the same argument and we can say something about what the relationship between A and B is. So if we take k to minus k, what happens is the measure is unchanged. So basically, from taking k to minus k in the d3k, we get 3 minus signs. We get another 3 minus signs if we flip back the limits of integration to how they work. So this is invariant under this change. So we just get e to the I k dot x I tilde star of t and minus k. And so that's comparing this expression. If we want phi to be equal to phi star, then we should have that phi tilde of t and k is equal to phi tilde star of t and minus k. And so that tells us that that gives us a relationship between A and B. And so if we just compare our expressions, if we look at this expression, so if we complex conjugate this and take k to minus k, we should get back the same thing. So that tells us then that B should be equal to A star of minus k. So that tells us that our original solution takes the following form. Okay, so this term, this exponential, is very nice. If we identify ek as k0, then this just looks like a Lorentz invariant product of two 4 vectors. We can write this as e to the minus I k dot x, where k naught is ek. So this exponential looks nice and Lorentz invariant. Over here, we've got the wrong sign. So for both terms, we have a plus I. But we can fix this by just doing the same change of variables k to minus k that we did before. So for this term, we can send k to minus k. And if we do that, we get something that's, or most of the pieces are starting to look Lorentz invariant. And all right, so we don't know anything about the a's, but the exponentials at least are looking Lorentz invariant. There is something that's clearly not Lorentz invariant, and that's this measure. So let's see what we can do with that. So I want to make the measure look Lorentz invariant. The obvious starting point is integral d4k. And we can put in a 2 pi to the 4th if we like. Now we want to relate this manifestly Lorentz invariant measure to the measure we've got over there. The natural way to try to do that is to throw in a delta function. And so if we want this to remain Lorentz invariant, it should involve a k squared. But over here, we set k naught equal to ek. So we'd like the delta function to do the same thing here. If we just put delta of k squared, that's not going to work. If we put delta of k squared minus m squared, if we expand that out, that gives us k naught squared minus k vector squared minus m squared. So one solution of that will be k naught equals ek. But we also have another solution, k naught equals minus ek. So this is k naught squared minus ek squared. So we can get rid of that other solution just by throwing in a Heaviside theta function. Now, you may worry about whether or not this is Lorentz invariant. But if we restrict ourselves to orthochronous Lorentz transformations that preserve the arrow of time, that will leave theta of k naught invariant. So this is invariant under Lorentz transformations that preserve the arrow of time. And so this, we do this integral. This just gives us 1 over 2 ek times integral d3k 2 pi cubed. This 1 over 2 ek just comes from the delta of f of x rule.
That is plus preserve.
To preserve the arrow of time.
Okay.
Sorry. And so if we define little a of k, which is just big A of k times 2ek, then we can write phi of t of x following manner. And here we have these ak and ak star, which tomorrow will become the creation and annihilation operators. And because we've gone through the effort to make the rest of this expression Lorentz invariant, we've got a Lorentz invariant measure here. We have Lorentz invariant exponentials. These creation and annihilation operators will create Lorentz covariant states, which will be very convenient for us later. So this will be our starting point for tomorrow, when we'll promote our fields and their conjugate momenta to operators. And so we've done most of the work in quantizing the theory and developing the Hamiltonian formalism and finding the solution to the Line-Gordon equation in this form. So we'll quantize the theory at the beginning of lecture tomorrow and then see what that implies.
We still put minus k in it? Or
No, this should be plus k. Thank you. All right. So yeah, so that's where we're going. So tomorrow we'll quantize the free field in the first few minutes, see what the implications, study the states of the theory for the remainder of the lecture, and then add interactions after that.
And that, but just staying in the classical field theory, how do I look to those AK? Like if I Lorentz transform. Oh no, it's okay. I transform X. No.
Yeah. So
Okay,
this is a scalar.
Okay. Okay.
Any other questions? All right. No, see you tomorrow.